260 RPM with completely automatic starting is the bestest version of the NEMA stepper motor powered earth field compass magnet motor is going to do. The NEMA 17 motor is powered by 8 AAA batteries. It's controlled by an L298N controller and an Arduino Nano. The bearing is a ball bearing snap lock fishing swivel, number 2 size, for 41-pound test line. When I spin the armature, it will turn or coast for over 1.5 minutes before stopping, so I don't think that I can reduce the friction anymore. The motor starts when the power wire is connected, going at 10 RPM, accelerating at 1 RPM per second, up to 180 RPM. After that speed, it accelerates at 1 RPM each 3-second interval. To use a stepper like this, you need to use interrupts. That is millisat, or millis. The wiring and control of the bipolar stepper motor is otherwise very simple. For the compass magnet motor to work, it needs to stay in phase. By phase, we mean the magnet has to be pointing mostly northwest. By keeping the magnet pointing northwest, the motor can push against it as it tries to point north. The armature weighs 1 pound 15 ounces. So physics students might want to compute the torque of the magnet in Earth's field. It is small, but very significant, as you can see, as the compass motor reaches a maximum speed of 260 RPM before friction on the bearing is too much for it to go any faster. The program will automatically accelerate the stepper to full speed, let it run for 1 minute, then stop it. Earlier, we tried to use a lamp and light-dependent resistors for feedback to keep the magnets in phase. However, this turned out to be unnecessary for starting the compass motor. It also couldn't help the motor go beyond its top speed, since its maximum RPM is limited by friction at the bearing. In a separate but related test, we kept the armature still and gradually accelerated the new NEMA 17 stepper motor to see how fast it could turn the magnets with 8 AAA batteries or only 12 volts. Without even getting warm, the motor got up to 500 RPM, and it could go even faster. As long as the speed changes gradually, the stepper motor performs well. However, if the speed changes by more than 10 or so RPM at once, it won't work much above 50 RPM. This was also an issue with using feedback to keep the magnets in phase. We did find a workaround at the time. The workaround was to count the number of steps the motor made and lower its speed by only 5 RPM after it passed about 80 degrees around from one of the 2 light-dependent resistors. Those are LDRs. Hopefully this information may be helpful to some since it wasn't readily available online. You may be wondering what a compass magnet motor might have as an application. Honestly, we don't know, but it sure is lit. Also, it right now illustrates the power of Earth's magnetic field. Buy our magnets from K&J Magnetics. They make it abundantly obvious in some of their information and videos that theory and reality don't always agree when using magnets. They are not a sponsor or are any way affiliated with my channel, but the information they provide is largely obtained by actual measurement and not just by calculation. One of the things I hear is that Earth's magnetic field is extremely weak and a poor idea to use for a motor. There is something called gradient. If you study calculus, you know what gradient is, but it's also geometry. Let's say you make a small boat and put a magnet in it. The boat won't move north or south because the magnetic forces are too weak. However, while the magnets won't move the boat north or south, they will turn the boat to point in alignment with Earth's north and south. Not only that, the more powerful the magnet, the faster the boat will turn.